I am very excited and honored to introduce Professor Allison Okamura today. She's from Stanford University's Mechanical Engineering Department. I will cut it short because, not because my voice is bad today, but also because like you probably know about her. You are all here to listen to her. I could spend a great deal of time to list her numerous achievements, awards, or like talk about her significant contributions to the science, technology, and also our society and field at large. But I know we are all looking forward to hear from her. I just want to talk about, just want to say something, one thing. The thing that I admire most about Allison is that she shows us how to balance an extraordinary career with a great life, like how to enjoy life while accomplishing so much. She is not only the leading figure in her field and driving innovation and advancing knowledge, but she's also a dedicated mentor who inspires the next generation of engineers like myself. And she's also an avid runner. So there you go. She also have great contributions to research, teaching, and leadership in our field. So this is a very powerful example to me and to all of us. So without further ado, there you go.
Thank you.
Please welcome.
Thanks so much for the introduction, and thank you, Melissa, for taking me running this morning through the park in the dark, where we encountered deer and lots of stairs. Yeah, thanks everyone for coming. It's a short visit, but I've had such a wonderful time already, and I heard that a future IRAS conference was going to be here, so I'm looking forward to looking at Howie. Looking forward to being back again in not too long, couple of years. All right, so I sort of debated on what I wanted to talk about today, but I heard there are a lot of people interested in wearables in this crowd, and so I decided to focus this talk on some of our work on soft wearable haptic devices for ubiquitous communication. And ubiquitous is just a stand-in for lots of different types of applications that I'll describe. So I want to start by highlighting some of my students and postdocs who are currently working in this area. I've had lots of former students, including Melissa Orta Martinez, who are PhD students in my lab working on things related to haptics. These are the folks whose work I'm primarily going to highlight in terms of the most recent stuff. And my lab is called the Collaborative Haptics and Robotics in Medicine Lab, or CHARM Lab. So all of my students are charmers. Okay, so what I'm interested in with wearable haptic devices is providing all sorts of different kinds of physical connections. And of course, an obvious one is human-to-human connections. During the pandemic, or even now when I'm traveling, Zoom or FaceTime with my family in order to have these interactions. And we'd like to make some of these more physical, more tangible, rather than only by video and sound. There are other types of physical interactions that would be useful if you're trying to navigate somewhere in a car and maybe you'd like to pay attention to the road rather than being distracted by looking away with your vision. Haptics or touch provides this alternative sensory channel through which you can communicate information. And then as robots become a larger part of our daily lives, in our workplaces and our homes, there may be more intuitive ways to interact with them and communicate by using the sense of touch. So the dream is to have these types of wearable haptic devices that can move around with you as needed and provide useful communications. So probably many of you, because I'm here in the Robotics Institute and you're familiar with the importance of touch, whether it be for human-robot interaction or human virtual reality interaction, or autonomous robots using the sense of touch. But I think it's always useful to have a reminder, because even if I'm a haptics researcher, touch is not always the answer. And so I'd like to remind you of some of the dual nature of sight and touch. So sight tends to be centralized, right? Like we have eyes in one place in our body where touch is, all over. Sight can be broad. I can stand up here and look at all of you. Whereas touch is sort of narrow. And also very active. So if I want to go over and poke Howie, I'd have to, first of all, be very physical. I have to walk over there. I'm not going to poke you, don't worry. And poke him. But also that interaction is through this like very narrow, like very local sort of physical information. And then there's sort of a cognitive and physical aspect. So what I'm going to say here is not entirely true, but it's maybe a useful first order thing in that with vision, a lot of processing goes on, and with touch, while a lot of processing can happen in order to interpret touch information, we also have reflexes and we have other things that happen at the spinal level for humans where we react without actually doing any processing. So there can be cases where you can react faster to something where you receive touch information compared to vision. So that's for humans. Then there's useful applications. Like why do we want to have haptic devices? There's these communications that I talked about before, but there's also sort of display of realistic information, which is also important. So whether you're a prosthesis user who has literally lost the sense of touch because you no longer have an arm and it needs to be replaced, or environments like very specialized cases where you're teleoperating a bomb disposal robot, teleoperating something in space, or you're a surgeon teleoperating a surgical robot. Those are also all special cases where people lose the sense of touch and they would like to have that realistic information reflected back to them. And now with virtual reality and augmented reality experiences, you don't have to have one of these special conditions in order to lose the sense of touch. As we embed ourselves more in VR, we're going to need to think about how is the sense of touch going to communicate realistic, useful information that might help you, for example, learn a task in VR and then transfer it to some real world activity. And right now, our interfaces are very simple. So this is a classic figure from the human-computer interaction community. Like this is how your computer sees you, right? Maybe you have stereo sound. These days with VR goggles, we can do stereo vision, but for the most part, it's monocular. And maybe you interact with one or maybe two fingers if you're talking multi-touch. And so how do we make our interactions with computers more generally, much more immersive and general? Now, in the beginning, the field of haptics, I say there's sort of two main branches that I think of in terms of people creating haptics for virtual reality and teleoperation. One of it very much comes out of traditional robotics and robot design. And these devices are great. They're kinesthetic haptic devices, which are basically robot arms that are highly backdrivable, and they apply rendered forces so that you can feel virtual environments. And they're fantastic, and they're very compelling, and they get used in things like robot-assisted surgery, hopefully is this next video. And by the way, if you're the squeamish type, that's not actual tissue, that is rubber and foam. So just showing how now someone is teleoperating a surgical robot. And a lot of the early part of my career was trying to understand how do we give this kind of net force feedback to the hands when you do teleoperated tasks or surgical training. But all of these are very limited in terms of the nature of contact with the environment. We're talking about displaying usually single point, single contact, resolved forces in multiple dimensions. And that is how the field of haptics really developed in terms of its connection to robotics. But I would say over the last decade or so, there's been a lot of interest in more cutaneous or skin-based haptic devices. And so on the left, the video that's playing, this is an oldie but goodie. Haptics researchers have probably seen this video a million times, and it doesn't seem to be playing quite right. But on the left, it's someone is having their finger anesthetized, and if they're trying to light a match before that happens, then they perform it very well. Let me see if I can get the other one playing. Yeah, video does not start at the right place. Okay, so this is now a video of someone performing the same match lighting task. The one on the right is the one to pay attention to, but she lost her cutaneous sensation. She has full vision, full dexterity, the muscles work. She's only lost sensing in the skin, and you can see how difficult it is for her to manipulate and pick up this match. And so this kind of example shows how difficult it is to do tasks without tactile sensing. And it motivated going beyond force feedback only in these virtual environments and also having cutaneous or tactile feedback. Get past that. So the challenge now then with giving haptic feedback, not as a resolved force through a robot, but now applied directly to the skin, is that the skin is complex, right? We have all these different mechanoreceptors, these sensors embedded in our skin, and their density and the type and what frequencies they respond to vary over different parts of the body. And also to build a device that stimulates the skin has been challenging. And so for decades, the haptics community has been kind of struggling to figure out how do we develop devices that are lightweight and portable, but still have kind of all of these degrees of freedom and properties to stimulate these mechanoreceptors. So what I'm going to be trying to do is take you through a path of some designs that we've had over the last 10 years, like focusing more on stuff we've really done recently to try to stimulate cutaneous mechanoreceptors and go towards this vision of ubiquitous wearable haptic devices. And my videos seem to be restarting at an unnecessary place. This is an example of an active surface. Just to start, if you want the most literal thing in the world, which is really not what we want to do in haptics typically, is you can imagine recreating objects, right? Having a digital clay. And when you do that and you touch it, you will feel both forces as well as the local skin distributed cutaneous information. But this is a really hard way to go, right? This work is 10 years old, and we did it using some soft robotics techniques with particle jamming and pneumatics. And it does create an effect, but we're very limited in what we can do. And in this case, we were trying to simulate hard lumps and different types of tissues, so it kind of worked for that specific application. But rather than literally recreating the world, instead, we want to use haptic illusions. The idea being that let's not really recreate the world, but try to trick the user into feeling something maybe beyond what you might expect given what's being displayed. So let's look at some ways to do that. All right, so one way, which is kind of relatively cheap, is using vibrations. So we have vibrations in our cell phones. I have one in my watch, but typically it's just used as an alert or telling someone about an event. So one thing that we've worked on, as well as some other labs around the world, is using asymmetric vibrations. Rather than just vibrating a sinusoid, you create a sort of weird shaped vibration that's been carefully tuned to give a net force in a particular direction. And it turns out that this can either feel like a tugging in a particular direction, or there's another thing that can happen, which people don't fully understand, is that when you feel these asymmetric vibrations, you can sometimes feel compelled to move in a particular way based on that vibration. So I'm not going to spend much time on vibrations, but because vibration actuators are, relatively speaking, kind of cheapest type of actuators, relatively low power that you can get, this is one example of a really nice haptic illusion that starts to be an example of something where you get more than you would expect out of a very simple actuator. Well, let's talk about a few others. Oh, first I want to talk about one other thing with vibrations. This is sort of an aside, but it's in a project I'm really excited about, which is not really about providing haptic feedback to users, but in looking at vibration feedback, we worked with collaborators that discovered that vibrating the hand post-stroke reduced spasticity. And this is a stiffening of the muscles, giving poor muscle tone after stroke. And basically, the idea was that even these simple vibrations can do something like have rehabilitative effects. So although I'm not going to talk much about vibrations, just wanted to note there can be these advantages to using vibration. But let's move on to fingertip skin deformation. And I don't know what on that video is resetting, so I'm going to move this one here. To show both this device as well as how it's used in virtual environments. So now we're moving away from applying net force feedback onto the arm, which requires large motors and a desk-based device you need to push against something in the world, to fingertip devices, which only stimulate the skin locally and thereby provide forces that feel like interaction with a virtual environment. And it turns out that when I do something like lift up this not very full bottle of water, and the point is it's not very heavy, that most of the information I'm getting is not from the muscles and joints, but actually from the stretch of my skin that tells me how much this weighs. So it turns out that in a virtual environment, displaying these localized skin forces can provide a very compelling sensation that you're manipulating objects, but without a big, clunky, expensive desktop machine. Now, I will say that this device is still pretty expensive. Those are like $600 Maxon motors sitting on there. It's like a little robot, little Delta robot that you're wearing on your finger. But we're starting to get down to the size and form factor that you might think someday could be mobile. But this work is older, from about eight years ago or so. And I'll get to what the newer devices look like. But first, I just want to mention how these devices, how effective are they? And one challenge we have in haptics is we run a lot of human subject studies, and this is really critical for us to evaluate the performance of our devices. But what happens a lot when we're trying to display certain properties, like the mass of an object in a virtual environment, is we tend to tell subjects, there's two objects, they differ in weight, and tell me which one is heavier. And you're therefore priming your subjects to interpret the feedback that they get as weight. And if you want realism, you want to understand how realistic things feel for this haptic device, you can't tell the subjects what they're supposed to be feeling. So we've been trying to do studies like this one, where we had two objects, but we didn't tell the subjects what had changed between them. We say, pick up this object, and then you tell us how they differ. And through that, sometimes they would say, oh, we changed mass, and the subjects might perceive that indeed that's what changed between them. But there are other cases, like when we changed the object's stiffness, how squishy it was when you squeezed it, it turns out subjects interpreted that like wildly differently. Some subjects thought we changed the stiffness, some mass, some friction. And people did a pretty good job with friction going to friction. And we sort of wondered about, oh, maybe our haptic device is not so great. And the punchline of this is it turned out that when we reran this study with real world objects, people made the same mistakes. So it wasn't actually the fault of our device, or it wasn't functioning properly. It's actually that there are these sort of haptic illusions at play. So humans perceive real world objects in this sort of way that you might not expect as well, at least especially if they're blindfolded. So it's kind of, there are these lessons learned about interpreting what you get out of these haptic devices, especially when you're trying to go for a new paradigm where you're maybe getting away from the very literal, like I'm going to apply a force that pushes on you, and you're trying to create these haptic illusions. You want to interpret them appropriately. So what we've been doing now is I have the word soft in the title of my talk, but nothing I've really shown you so far has been soft. So we're going to start traveling into the land of the soft. So we really are believers now in this method of skin deformation haptic feedback, and I think many people in the haptics community are making devices this way as well. But like I said, $600 Maxon motors, how do we actually get these to be cheaper, lighter weight, and something we can actually put out there? So we tried making origami devices. We have tried 3D printing with some semi-soft connections. And more recently, and I have another slide providing the details on this, we're creating fully 3D printed wearable fingertip haptic devices. So I think I'm going to skip over this one and just get to the 3D printed one. Yeah. All right. So if we're going to make wearable haptic devices, we're taking a cue that are lightweight, as lightweight as possible. One way to do that is to try to offload the actuation. And this is hard to do with electromagnetic actuators because getting transmission of electromagnetic actuator, to get that information, say, from your backpack to your fingertips is really difficult. But if you do it with pneumatics, the transmission can happen in a pretty straightforward way. So it is cheating in a way because the full actuator, providing in this case the pneumatic power, is not mounted on the fingertip, but we are able to get a transmission from an actuator that's further away. So in this case, this is a haptic device that has been fully 3D printed in Form Labs using one of their standard semi-soft materials. And it's set up to have these actuators that close when there's a vacuum, or it bends when there's a vacuum. And so these actuators are set up in a pattern that mimics the kinematics of an origami water bomb pattern. And that gives it actually 4 degrees of freedom. So more than any previous wearable fingertip haptic device, it has 4 degrees of freedom, giving you the shear directions, the normal force, and the twist. And that allows you to very compellingly interact with virtual objects. And it turns out twist is really useful to have, and I'll screw the cap on for this. So at first we were really interested just in the 3 directions of normal force and then shear in 2D. But it turns out when you are manipulating objects in a virtual environment, it's very common for things to twist within your grasp. And so we felt that that twist degree of freedom became important. So it was great to now have a 4 degree of freedom device in this relatively compact package. So that's starting to get into soft haptic devices for the fingertip. But all the pictures I showed you in the beginning, we had haptic devices on the wrist and the upper arm and not on the fingertip. And there's some important reasons for wanting to do that. One is that as we're more interested in augmented reality, you want to be able to touch real world objects and also touch virtual objects. And you also want to have good hand tracking. And it is challenging if you've got weird clunky things on your fingers that also occlude other fingers and change the shape of the so-called fingertip. It's very difficult to do tracking. But also if I want to go and touch this real world object and then go and touch a virtual object, if I have something stuck to my finger, then I can't do that. With visual information, you kind of imagine augmented reality is fairly straightforward, right? You can overlay things, but you can't really overlay touch. I'll say that with a caveat because we are doing research to try to figure out how we could do that, but it's very difficult to overlay touch. So can we move things off of the fingertips to other parts of the body? And so you touch an object, a virtual object here, and you feel it here. Can we actually create a haptic illusion of someone feeling that virtual object and still allow people to touch real objects? So that's one purpose. Another that I've been talking about with Mark Kokoski, who's been doing a lot of work with tactile sensing arms on robots, has been enabling full body telepresence. And with the proliferation of humanoid robots, I've also companies like Figure AI and others that they're very interested in providing a more immersive telepresence scenario for people teleoperating humanoids. And so if you're doing something like Mark's favorite example is you're reaching for the salsa in the back of the fridge and you're bumping other things with your arm on your way in, these other contacts become pretty important. So the idea is what kind of haptic devices are needed to give telepresence for this more full body experience. So those are all some motivations for why we want to move off the fingertips and onto other parts of the body. But this is hard. So one is I mentioned earlier on that the mechanoreceptors, the cutaneous mechanoreceptors differ depending on where you are in the body. And in particular, in the glabrous or non-hairy skin of places we have usually a higher density and certain types. And then on hairy skin, you'll have usually fewer mechanoreceptors and also different types. And that's pretty well known. I think there's another issue that it's maybe obvious once you describe it, but it kind of took me a while to realize that this was a problem, which is that we are used to doing active touch with our fingertips. And I think I have to acknowledge Bobby Klatsky for explaining this kind of thing to me earlier in my career, that active touch is super important for haptic exploration and learning about the environment. So when you're going to say, feel texture, right, you're going to move your hand in the correct way to excite the mechanoreceptors for you to get the necessary information. And our hands are designed by evolution to allow us to do that exploration. But now if we give feedback here in this other part of the body, we're not used to kind of exploring with our hands and then feeling it somewhere else. And we're definitely not used to, exploring a surface by contorting your body and feeling it this way. So I don't have any, grand answers here, but just want to kind of have you think about this active touch versus passive touch issue. And it's not always easy to kind of relocate haptic feedback and assume that people are just going to be able to interpret in the same way, both because of both of these issues that I put up here. Just another quick example, and this is something we looked at in part because we were trying to do haptic feedback for people with spinal cord injury and such, is that, as you move away from the fingertips or move up the body, you get poorer and poorer tactile resolution, and this has been tested in both patient populations as well as healthy people. So let's now talk about these haptic devices that are off of the fingertips and how well they work and what are some of the design challenges. So early on, we were making very simple wrist devices and trying to quantify how well people could do in virtual environments when they got the feedback here rather than at the fingertips. And it turns out people could do this task. They could, the thing that's on the fingertip here is just a tracking system. It's not haptic feedback. So my postdoc, Mina Sarat, she would touch these virtual objects, move the fingers over them, get the feedback here. And people could do just as well in this task that I mentioned earlier. They could identify mass and stiffness and friction, and they could get the just noticeable differences. So if we kind of scaled up the forces on the feedback so they were noticeable enough on the arm, people could do the task. So just because they can do it doesn't necessarily mean you should do it. I wouldn't call it, although what we want is a haptic illusion, I wouldn't fully call it a haptic illusion. I think someone can work at it and they can pay attention, but it's not like you explore with your finger, feel the haptic feedback here. You're not tricked into thinking it's happening at the finger, but you can learn to do it. So I think this is still an open question for us. Can we truly make it an illusion, and what would it take to do that? That's still future work. There are other questions that if you're going to give haptic feedback relocated to other parts of the body, how do you do that? There's sort of a natural pattern that like maybe the thumb should go to here and the index finger should go to there. But we wanted to try other different combinations. And what was interesting, we found, so this is my student Jasmine doing this virtual task with haptic feedback on the wrist. And one thing that we found interesting was that when we took both points of touch and we fed it back to one location, people could perform just as well at simple manipulation tasks. And maybe it's because the manipulation tasks were simple, but it did show us that, yeah, maybe people can really interpret this information pretty well. They can learn to do it quickly, and that's nice. And maybe that decreases the number of degrees of freedom and contacts that we actually need to display on the arm. But definitely from a more subjective point of view, our participants said they preferred a mapping, which is kind of the one that you would expect, where fingertip goes to here and thumb goes to here. And people could still do this task pretty well with this feedback. So all my videos are not resetting well, but let's see if we can play these. So after making these earlier devices, so starting about 6 years ago or so, we decided that we wanted to get past the requisite how we made our soft robot part to the actual device. Here we go. So we started playing around with, if we want to make these devices more comfortable so they'd be soft and wearable, how can we do that? And I'm going to show here, these are 2 videos of things that didn't really work. I mean, they're kind of fun, but we were really trying to build on like what we knew from the soft robotics community and put that onto the body. So this one didn't really work. It's using a classic fiber reinforced elastomeric actuator approach, or that's sort of this freeze. But in order to get that contact point to move back and forth, you had to push against something. Like there has to be some kind of reaction force. And that meant having this clunky frame that you would push against in order to provide shear on the skin. And so that wasn't great. We still managed to publish it. And then another thing that wasn't great we managed to publish was, some of you might know our lab has been doing these things with soft growing vine robots. And we thought, what if you could put these little soft growing vine robots in a bracelet and then have it grow out, wrap around the arm and then squeeze. And that's what this thing is doing on the right. You know, this was more just an exploratory idea. It turns out that when you have that much curvature, it's really hard to put it back in the bracelet. So we had no way of retracting it. And the squeeze, we really couldn't get like more degrees of freedom of information out of it as much as we had wanted. So these were a couple of things that we did, which were kind of fun, but not, you know, not ideal. And then, let's see, on the left here, we were still trying to do this fiber reinforced thing, but more carefully. But once again, we just still found we had to surround it with this 3D printed frame because there has to be something that takes up the reaction force. If you're going to push down or to the side, something else has to push against it. So it did work and people could use it, but it's not particularly comfortable and it wasn't our dream of a soft wearable device. And then this one I already showed you was great, but we couldn't find a great way to translate this kind of stimulation to the arm. So let's see. So one of the first things that we had done with arm-based devices that was more comfortable was some work on social touch. At the time, Facebook, it was still Facebook in those days, not yet Meta, was very interested in sort of haptic emojis. And they actually funded a good number of haptics researchers around the US to explore how you could display some of these social touch cues through touch. And one of them was, for us, that we were very interested in was the idea of stroking, right? This is me stroking my husband's arm. So I did not subject my graduate students. So the idea here is that we do not want to literally take a robot finger and stroke it down the arm. And it turns out that this, you know, this sort of stroking behavior is actually really important as a social touch. It's calming, it can help people address, for example, they use these kinds of touches to help people prepare for surgery. It's an important one. And so the first thing that we did, when Heather Culbertson, who's now at USC, was a postdoc in my lab, was try to figure out what pattern of touches would work to feel like a continuous stroke. And this truly was a haptic illusion in that you'd have these individual contacts, but people would think that it was continuous. And also we would have them do things like rate pleasantness. And this was sort of a soft haptic device in that, you know, it's a soft surface that wrapped around the arm, but the individual actuators were voice coil motors. And that was not great because the voice coil motors, they heat up and overall they do get quite heavy. So here's some other, oops. I don't know why that's, but let me see if I can get it. Yeah, so we tried all sorts of different devices to try to give this continuous stroke illusion. The one at the top is the one with the voice coil motors. I'm not sure it's playing anymore. One pass through them. And then the one at the bottom is another example where we thought, like, instead of just touching one by one, could we kind of stroke and sort of scoop in and out of the arm? And that also, like, it didn't really seem to matter how much, I guess, detail we provided with any of the individual contacts. The main thing was to get the timing right. And so we got this timing right by running a series of social touch experiments where we actually had pairs of subjects. We had two types of pairs, pairs that were people that knew each other really well, best friends, romantic partners, etc. And then we also had, and I'm just only going to show you the results from, from this group, but there were also folks who were strangers as well. So in this case, my student Sophia is wearing a capacitive tactile sensing sleeve. Another student is trying to convey feelings like, I'm so happy, it's okay, and pay attention to me, things like that. And we recorded data from a bunch of different social touches, and then we mapped those onto the arm in order to try to get the timing right. And it turned out that when we were recording touches from people who knew each other well, the touches actually would make sense. So if we took recorded touches and then we replayed them on the device, people could recognize in terms of valence, kind of happy, sad, and arousal, sort of sleep to excited, that all of these social touch cues would kind of fit into the right place on that map as you would expect. It turns out that when we took social touches from strangers and tried to display them, it did not work as well. Like, people know how to touch each other if they are actually close, which I think is kind of reassuring. And then the social touches, and then we, that were, say, between a couple of friends, and then we played them back to another person who was a total stranger. Their data matched similarly in terms of recognition to when you have two people who are strangers touch each other, which is interesting. So that device and the social touch was fun and interesting, but it still wasn't truly a soft device. Like I said, the voice coil motors are a little bit heavy. They are not super comfortable. They weigh quite a bit. And so we wanted to go back to this idea of using pneumatics from the Fingertip, which was pretty successful for the Fingertip haptic device. But we were having this problem of when we put wearable devices on the arm, we had to have this rigid backing in order to provide the reaction force. So I'm going to spend a few more slides in this talk talking about the work of Cosima Dupasquet, my postdoc, who is on the faculty job market this year. She was very interested in using variable stiffness knitting. And this, the using knitting in wearable devices has recently become quite popular. I think Vanessa Sanchez, who is now at Rice University, was probably leading the way in doing this. And we were very much inspired by her work. But for us, more specifically, how do we figure out how to provide these reaction forces for haptic devices? So we started working with Skylar Tiviz's lab at MIT, who was doing a lot of work with machine knitting. And the great thing about it is you have so many materials you can choose from and make all sorts of complex shapes. These are some examples from Skylar Tiviz's lab. And we're combining that now with pneumatics. And the pneumatics are very simple. They're just little inflatable pouches that we 3D print using semi-soft material. So on the left, you see one that's not inflated. On the right, there's one that's inflated. We put them inside some knitted materials. And here, the gold part is stiff material. We've knitted it to be stiff. And then the blue part is soft because we've knitted it that way. And that means when you inflate, you actually have that rigid backing, and yet the whole thing is knit. And so in this sort of continuous way, it becomes very comfortable to wear. And you'll see this more in some future devices and videos. So here's looking at the knitted result, where you have this dark area indicates a sort of soft knit area. And then when we inflate the pouch, it pushes down onto the skin. So how did we do the knitting? So there's two ways that you can change the stiffness of the knit. One is through topology variation, right? You can change the structure of the knit itself, the type of knot, the pattern, the number of layers, and you can get some pretty dramatic differences. But the dramatic differences there, it turned out, wasn't really enough for us. So we also did material variation. Now, the nice thing about knits, like the weaving that I saw in Melissa's lab this morning, is you can bring all sorts of different materials. And the colors here don't really matter because it's haptics, but it's very nice to be able to bring in different materials. But one of the coolest insights that Cosima had was that we could use thermoplastic fibers embedded in the knitted material. And then if you heat them up later, they can become very stiff. And so by having different weights of these thermoplastic fibers embedded, we're able to come up with orders of magnitude changes in stiffness when you put it all together. So all of this was put together in a wearable haptic device. I won't talk much about it, but we're also really working hard on making the pneumatics portable. And so we are now getting to a point, I was a little worried when we did this whole thing with pneumatics that we're just backing ourselves into a corner and pneumatics was never going to be a real solution. But I think it's possible now. And companies like Meta Reality Labs, they are actually investing a lot also in making portable pneumatics. So it's not, beautiful, but it truly is a portable pneumatic device now that can run all of these different tactors, which are inside of this sleeve. So what we're doing is we're having multiple layers, different stiffness in some layers, and it's key that the backing part be stiff. But the great thing about knitting is that stiffness can be very much continuously graded from one location to another. So one of the biggest challenges in soft robotics is getting soft and hard things to stick together. And so instead of trying to stick those together and glue them or screw them, whatever you do, now you have this continuously knitted material, but parts of it become hard when you heat treat them due to the thermoplastic fibers. So this makes it pretty functional. I think I'm going to skip over this assembly detail and just show this video of our knitted sleeve. And we're using it for multiple things, but in this case, it was social touch. And these actuators can display 40 newtons, which is a lot of force. And all the same patterns that we could do with voice coil motors, we could also do with these simple pneumatic system. That's mostly what maybe I'll show a few things. So all of these same social touch patterns that I talked about before that we measured based on human-human interactions can also be mapped onto these. And so you can get these same haptic illusions of feeling a continuous stroke, even if you have individual touches. And my postdoc is thrilled because this work just got accepted to Science Robotics a few days ago. And so you guys get the preview. And so, the vision is this type of haptic device could be used in teleoperation, it could be used for navigation, for sports, it could be used for prosthetics, and lots of other things. So I'm just going to end briefly with just some challenges for this field. Where we've moved away from these traditional desktop robot-like haptic devices to wearable, soft, cutaneous simulation haptic devices, and there's still a lot of work to do. So wearability, we still need to do more. Our knit devices are pretty comfortable, but they're still pretty thick. And so you can get sweaty in them. It'd be great if we could make them more breathable. So comfort, encumbrance, and then with the pneumatics, we still have an issue with sound. Like there are approaches like you can pump something up separately or have a canister of compressed air, but that only lasts so long. And even when the air comes out, it makes some sound. So we need to address the issue of sound. So these things might be a choice of actuator, structure, and material. And again, our challenge has really been like, how do you create the reaction forces and still have it be a comfortable device, right? For every action, equal and opposite reaction. We found a way to do this with knitting, but that's only for normal forces. We don't think this really holds up very well in shear, and we'd also like to display shear forces. So we really need to keep working on what are the structures and materials that will let us display shear forces. And now that we have these types of devices, we're just scratching the surface of what we can do with interaction design, right? Right now, we're only, again, doing these normal forces. But what about the degrees of freedom? What if we now want to integrate, real and artificial touch like we'd like to do for augmented reality? And then also multi-modality, right? There's this whole issue of combining vision and touch and sound. And while people have done this quite a bit with single point force feedback and vibration feedback, there hasn't been a lot of work, with the exception of Marcy O'Malley's work at Rice, really looking at multimodality in terms of touch distributed throughout the skin. So a lot of exciting work to be done that is drawing from robotics, psychology, and materials and people in the soft robotics field. And with that, I'm going to end by thanking all my students and sponsors and thanking you.
For the talk, I'm pretty sure we have a lot of questions. You can have a shot for me, so here we go.
Yeah, thank you so much for a great talk. I was really interested in what you were talking about haptic feedback on the fingertip. The sense of touch of objects is actually very nuanced and complicated. And going back to the match task, I think it matters, like specifically where on the finger you're feeling the touch. It's some of our complicated, seeing in a lot of devices, and it's things like these left right down. Is there a path to create some of that?
Great point. Like I gave that video example, but a lot of that is about contact location, right? And people have designed pin arrays and even some tiny pneumatic displays, like kind of like the thing for our sleeve, but very tiny for the fingertip as well. And that works. I don't think that people have really found a way to test those well for these kind of nuanced interactions, but I think it's a direction that the field is going. At the moment, it's kind of nice to be working with the arm because there's lots of unused skin real estate, right? Like we're not, we're not including the fingertip. We've got lots of space, and yeah, we have to display larger forces. And although we could make those devices smaller, we want them to be big because if the 2-point discrimination, on the arm, that is, you can't. The 2 points of contact have to be pretty far apart before you notice that they're 2 points and not one. Like we actually want them to be big. And so that kind of makes it easier to design. So how we can, make this work on the fingertip, especially, I think is an open problem, but people are working on it. And there's all sorts of smart materials now, Hazel actuators, other types of smart material-based actuators. That might get us there if you're willing to use 6,000 volts. Great point.
I also had a much less sophisticated question on the fingertip. I was curious when you were talking about the twist axis, both like if there are any limitations that come from like the limits on your joint angles, like you could only twist a few degrees, it looked like, and also if there were limits on telling twist that is either force that's applied or actually a slip, which I think would appear different.
Yep. Great point. Absolutely. So yes, our device can only rotate a little bit, right? So if I want to display something twisting like this, it can't do that. I think the idea there is typically in a virtual environment, we don't want someone to drop the object. So what happens is if you have like a friction limit surface and there's twists that kind of breaks the friction and makes it harder to hold on into other degrees of freedom. So the idea is that if it starts to rotate, you can feel that, and then you can ramp up your grasp force and prevent it. In terms of slip displays, there have been all kinds of little clever haptic devices, like little balls that roll on the finger and such to create the sensation of slip. But they haven't really been integrated with these other types of more multi-degree of freedom haptic devices. And there's other sensations and I think slip is one of them, where you want to know that slip is happening, but people don't even do a great job at, say, detecting direction of slip. Like we once did a study where we tried to create slip in different directions, and there almost had to be a 45-degree change in the direction of slip for someone to even notice the direction of the slip. And so there may be vibrations or other kind of illusions that we could apply that would give the sensation of slip. Not entirely sure, but if slip was very important for a task, which it might be, because the challenge is in a virtual environment, ideally, or an augmented reality environment, you want to let the person do whatever they're going to do, right? And the system should react appropriately. So that's for the general case. Yeah, that hasn't been solved. But if you're trying to, say, train someone to do a particular task, maybe you just need to get to the limits of what's appropriate for that task. And that probably wouldn't include slip, because in most manipulations, we want people to keep control of the object. Yeah, great question. Yeah. Absolutely. You want us to solve all the problems. That's great. No, yeah, totally. You are highlighting like all of the challenges. Absolutely. So, so one way to think about it, I guess, for the fingertips of interaction, we do think maybe you could map multiple fingers to here, but we haven't tried that yet. I don't know if anyone's tried that yet. Anyone knows, let me know. I think that would be super interesting. Like we've done just 2 fingers on the wrist, but now that we have more degrees of freedom, it would be interesting to try to see if people could map those degrees of freedom more globally. But each finger does interact in a relatively simple way, slip notwithstanding, right? Like, and changing contact condition also notwithstanding. But if you're thinking about, normal force and shear, we can probably get to a point where we design devices where you can get normal force and shear, at multiple locations. I think the big question is going to be, can we interpret that information on these other locations? And we haven't really built the devices to test that yet. Learning curve wise, with all of this social touch work, we were trying to do things that were immediately intuitive. Like we didn't train people. We didn't say, feel this, that's supposed to be this touch. And then later on check recognition rates. We just said, feel this, what do you think they're trying to tell you? Trying to do this kind of open response paradigm, seeing what's natural. While there are some populations, especially like in clinical or medical scenarios where patients or people are very motivated to learn, for the general population and doing things like social touch, ideally a user would not need to learn. So we're trying to get away from learning because we don't want people to have to do that. But there are maybe scenarios, especially maybe in addition to the workplace, in addition to medical, like there may be sort of workplace scenarios where people are also motivated to learn, but ideally not much training would be needed. I'm not sure if I hit all your points, but hopefully some of them. Thanks. Yeah. I think that's you. Yes.
One of the things I was curious about the
Yeah, that's a good question. I mean, right now, taking lots of data and learning on that is a pretty popular thing to do, but some types of data are very hard to collect, right? I mean, potentially we could take the data set we already have, which by the way, our social touch data set is publicly available and anyone can download it. I mean, we've already done some kind of severe mappings. We let people touch anywhere in the arm, like I'm so excited versus calm down. And then we mapped it all to just this one part of the arm because our haptic device didn't cover up here. So it wasn't totally literal. It was a combination of doing some learning and then doing some, actually like design work to do those mappings. And it would be interesting to see if we have mapped those to other parts of the body, would they still make sense? Because while we took some liberties here, it was still generally the right part of the body. I don't know if I'm going to feel the same way on my cat if I get those same signals. And we haven't tried that. That would be fun. Yeah. So I don't know the best solution, but right now we do have some data and hopefully people can use it. Oh, okay.
I'll start from here.
Okay.
Okay.
Okay. Visor. Yeah, in our case, our social touch cues didn't have very high frequency vibrations in them, but you could absolutely do that. And you don't necessarily need another actuator. You can also get the pneumatics to do relatively high frequency vibrations. So while we could do that, our current data set didn't have that information, but we could try it. Absolutely. Thanks. Try to give quicker answers now.
Giving feedback on other than different tips.
Uh-huh.
Have you ever considered the case of like amputees? Because
Yeah.
you're giving the feedback on the same side.
Yeah.
What happened when
Yeah.
you're giving the feedback on the left
Yeah,
side or right side?
That's a great question.
Not enough part to give on the feedback. That
Yeah.
doesn't confuse the users on the feedback.
Yeah, we haven't tried that. Paul Keating at University of British Columbia did a really interesting experiment with haptic feedback on surgical robotics. So this was still on the hands, but to like break. So if you apply large scale fast force feedback in teleoperation, you have stability issues. So he like swapped the hands, like he gave haptic feedback on the other hand to like break that closed loop. And people still did pretty well. So I have no idea if that would work for social touch and other things, but yeah, we should try that. That would be very interesting. I mean, already with our device, we were more like plain haptic emojis. It wasn't an interactive task, but it would be interesting to now to start to actually map and then try that cross display. Yeah, that would be cool to try.
Lovely, lovely talk. I wanted to hear more about it. Like,
Yeah, great question. I mean, I think the eventual goal would be to somehow use this to make people's lives better, right? Like if your child misses you and you're, either can't touch them because you have COVID or because you're far away in distance, like, can you maybe improve someone's mental health by giving them a stroke on the arm? And people have been looking at this for medical scenarios as well. But then like beyond that, there's, what are the sort of measurable, more direct measurable outcomes? And so recognition is one, but Kara Nunez at Cornell is a former student from my lab. She's been doing things like measuring people's heart rate and seeing galvanic responsive ways of like measuring stress to see how these social touches have effects. So, that I think is a laudable goal. But probably the more practical thing, which is separate from social touch, is how can we improve training based on augmented reality and virtual reality experiences? How can people translate those to being able to do real world tasks? That's sort of a very different thing from social touch, but almost easier because I think those are more measurable. Thanks. One more. And then finally, Howie, right?
Yeah.
Okay.
Howie.
Good.
Say made the hour like go by so fast. I think interesting.
Like you literally don't have tactile sensing because your arm is gone. Yeah.
How close do you think that pneumatic actuated sleeve is to like
Yeah, I think we're pretty close, and probably some of the bigger challenges are actually the sensing on the artificial hand side, right? There's a new hand ERC that I understand some people here are involved with, where they actually are really looking at haptic feedback. So I think that is definitely a goal for the research community, but it involves just as much on the hand side. How do you do the sensing as it does on the feedback? And so hopefully you all will, Nancy and Lisa and others will solve that problem.
Yeah, look.
Oh, okay. Great.
It's okay. I'll consider it.
Yeah, now we all want to hear it.
So I was inspired by that, what you anesthetize, what you with anesthetizes that
Yeah.
let it match.
Mhm.
And I was wondering if the sensors that were deprived were actually in the muscles, because not only can we feel and touch, but when we're pulling on something, I'm sensing things in here
Yeah.
too. So first, is that right? And then the other questions is, where does that fit in to this whole haptic picture?
Yeah, so so the sensing in the muscles and the joints kind of falls into like the larger issue of proprioception, like knowing where your body's in space and large scale forces. The lighting the match is a very relatively low force activity. And maybe it's not even the lighting the match part, like picking up the match and manipulating it. The forces are really minute. And so they're so small that your proprioceptive system isn't really, it's not really coming into play. Just like because my water bottle has hardly any water left on it, it's really lightweight, and I'm getting way more information from my cutaneous sensors than I am from muscles and joints. And so it depends on the scale of forces. I think if you're manipulating something large and heavy, then like you're saying, absolutely these other parts of perception come into play, but that sort of proprioceptive kinesthetic perception is just not really in action when you're doing these very fine, lightweight manipulation tasks.
That's what you have your job and I have mine. Thank you. Thank you for the fine talk.
We are in a very tight schedule, so let's thank our speaker. Thank you so much.